Today we're celebrating our 1000th Computer Channel subscriber. And as a reward, this video is a special request from them. Here we've got some gold foreign currency left over from an exotic vacation. Sadly, we will be unlikely to return to the beautiful country for a while. But the coins are made of cutthroat nickel, which is 70% copper, so we'll have to put them to a chemical use. Let's first do a quick test. This is 68% concentrated nitric acid. And a coin. Yup, this works. The brown fumes are nitrogen dioxide. With a boiling point of around 20 degrees C, it should be possible to prepare liquid nitrogen dioxide. So we've rigged up a special apparatus. We've got the 500 ml 2-neck flask, and we've got the large neck stoppered and the small neck leading to an adapter. The large neck will fit our coins. The adapter then leads to a tube and condenser. And then we've got the receiving adapter and a small flask sitting in a bowl. We've also got a takeoff using an old nasty bit of plastic tubing. And this leads up to our extractor and means we hopefully won't die of nitrogen dioxide poisoning. Use ventilation. This stuff is very toxic and unpleasant. We've got some loose cotton wool in the adapter, and we've covered this with a few centimeters deep of anhydrous calcium chloride. This will hopefully absorb moisture and stop any acid aerosol from getting into our product. We've got the condenser hooked up to ice water for cooling. And we've got the receiving flask in a bath of ice and water. Okay, so that's our setup. Not too complex. Here's our large-scale acid. 100 ml of 68% concentrated nitric acid. Let's get this into the flask. And now we're just waiting for the temperature in our ice baths to drop nicely and level out. The reaction is exothermic, so we've got the reaction flask sitting in a bowl of water to moderate the temperature a bit. Okay, let's get on with the show. The reaction kicks off fast with lots of brown nitrogen dioxide gas coming off. At the other end of our apparatus, we've initially got a lot of brown gas escaping and being drawn away by the extractor. And we then start to see the gas escape die down and a dark-colored liquid is condensing into our receiving flask. The reaction in the flask is vigorous and produces quite a lot of heat. The liquid collection starts to slow down after a few minutes. Looks like our drying setup is working as well. And our ice baths are still nice and cold. Distillation has stopped, so we're going to add a couple more coins to the flask again. As before, we've initially got some brown gas emitted. But then soon after we start resieving the liquid again. This is rather interesting, and we'll come back to this later on. Nitrogen dioxide actually exists in an equilibrium between the single nitrogen dioxide species and the dimer species, which is known as dinitrogen tetroxide. At lower temperatures, the dimer species, which is colorless, is favored. And you can see here in our apparatus, as the gas passes into the chilled condenser, it changes to a paler color. We've also got a little of the liquid condensing at the top here. You can see it's actually got a blue color to it. The reaction with nitric acid also produces some nitrogen monoxide, or nitric oxide. Although it's not supposed to happen except for at low temperatures, we seem to have some of the nitric oxide reacting with the brown nitrogen dioxide to form dinitrogen trioxide, which is then obviously soluble in the liquid nitrogen dioxide. Although liquid nitrogen dioxide contains a lot of colorless dinitrogen tetroxide, when pure it's still a dark brown color. Dinitrogen trioxide, however, is blue. You can see the blue color quite clearly in the receiving adapter. We added 2 more coins, making 6 in total, and continued to collect the blue-colored distillate. The temperature of the reaction has raised our water bath temperature a bit, but it's under control. No more distillate coming off now, so it looks like we're done. We quench the reaction by adding 100 ml of cold water. This reduced the gas evolution down to virtually nothing. We then prepared a solution of sodium carbonate in water. On adding some of this a little at a time, and restoppering the flask, we were able to purge most of the brown gas out of the apparatus. This is a little safer and easier to dismantle now. Here's our product. About 6 or 7 ml of a dark blue liquid which we think is mostly nitrogen dioxide, but with some dinitrogen trioxide dissolved in it. It seems to be fairly stable when cold, and we didn't notice any pressure build up in the flask. With the white background you can see the blue color a bit more clearly. Okay, now let's do some experiments. First, dripping some onto a glass dish at room temperature. It quickly evaporates, producing heavy brown nitrogen dioxide fumes. And soon disappears without a trace. Here's some cool water. It doesn't stick around for long. As it reacts with the water, it heats up, causing it to boil off as brown fumes again. The resulting solution containing nitric and nitrous acids is strongly acidic, as you can see here. If this forms inside your lungs, you are in whole worlds of trouble. Now for something more exotic. Here's some solid hydroxylamine hydrochloride. It's a very vigorous reaction. We decided not to add the solid to the liquid as it could well be explosive on a larger scale. Now some ethanol. Very pretty miniature explosions. The liquid remaining has a very strong aldehyde aroma. That was pretty, so let's do it again. Next, here's some benzyl alcohol. Not as vigorous as ethanol, but the liquid heats up and there's a very strong almond aroma of benzaldehyde produced. Not a very practical synthetic method though. Finally, ice-cold potassium hydroxide solution. Very vigorous, and it looks like most of the product escaped as gas. Well, that's all our experiments done and our product used up. But it was a very interesting experiment. We're intrigued by the way that the brown nitrogen dioxide gas comes off the reaction at first but doesn't condense. Even when the condenser is already ice cold, it takes about 10 to 15 seconds and then the blue liquid is seen. Maybe somehow it takes the generation of nitric oxide to get the product to actually condense. Although nitric oxide has a much lower boiling point, perhaps it forms some sort of azeotrope or adduct with nitrogen dioxide and dinitrogen oxide, which is what we end up with here. We're interested to hear your ideas and theories. Thanks for watching.